All right. Good morning, everyone. Is everything ready to go?
Yes.
All right. Good morning or good afternoon, good evening. All right. Today, for the first half hour, maybe 40 minutes or so, we will talk about some of the next steps in scientific workflows, specifically with DataJoint. And I'm definitely interested in hearing questions because this is, by definition, a very open-ended discussion. And a lot of things are in development, and we will be responsive to the ongoing developments in the field to adjust these plans. So let's talk about it. So this is the outline. So first, let's talk about the general trends in neuroscience, what drives some of these developments. And then the development of the framework of DataJoint framework, as well as other similar solutions or compatible orthogonal solutions as well. Then DataJoint elements are specifically to a collection of complete solutions for neurophysiology, and PsyOps, which is the the managed services to automate and streamline the operation, hosting and operation of complete workflows. So these are some of the general trends that drive these developments. So generally teams or neuroscience is responding to increased complexity by aggregating science or organizing science as team projects with multidisciplinary collaborations. And these tend to be highly distributed projects, especially we have been forced into a more distributed mode by the pandemic and actually increased our collaboration capacity. The complexity of experiments, it's becoming clear that to understand the brain, you have to catch the brain in complex and study the brain in complex behaviors in awake mice or awake animals in general, more on the system level involved in complex behaviors. And with multiple modalities of data collected at the same time. And increasingly, to increase the rate of learning and discovery, the loop of data collection, experiments, hypothesis making, and modeling needs to be tighter, and we'll talk about that. And artificial intelligence or machine learning in the loop is a very common proposed approach in many different current proposals. So I think this trend will take over a lot of future experiments. Another tendency is the development of a huge investment in development of neuroinformatics resources and infrastructure. And INCF is the prime example of coordinating these developments and making and helping us become aware of all the parallel developments across the globe. And this includes frameworks and data standards, a lot of tools, data analysis tools, repositories here, archives, catalogs, and platforms. Especially with the rise of cloud platforms, and many online tools that are available to us. It's kind of a Cambrian explosion of available architectures, platforms, and navigating through this becomes pretty difficult, especially if it's not your primary focus, if you're focusing on studying neuroscience. Another pressure is reproducibility, and so funders and publishers require making the data fair, findable, accessible, interoperable, and reproducible. And so increasingly, to get a grant, you have to also compile a plan for disseminating the data, making all the data, or at least a big portion of it, available for others to reproduce the findings, or maybe mine the data for future for additional findings. And then, so we are undergoing a huge revolution in how computing is done. One characteristic of this is there are multiple paths, and there are many decisions to make. And so there are tendencies to standardization, but there are also tendencies toward trying many different things. And so data and computations are becoming scalable, so that if you have a quick burst of computing demand, that you can deploy scalable architectures and complete your projects without a heavy investment in infrastructure. Containerization, virtualization basically makes computation very portable, makes it more like a utility or than like a specific machine or system. And increasingly, technologies are becoming distributed. So it's not all centralized in a specific platform. It can be distributed in the community and still act in an integrated way. So these are some of the changes, some of the trends, and so we have to adapt to them. And for neuroscientists or for working scientists who need access and ability for computation and data management, but who are focusing on the science, they need proper tools and infrastructure and framework to have access to all these resources. So one increase in complexity, just as an example, I'm using microns as a example of a project at Baylor College of Medicine, partially because I participated in it a couple of years ago. And just to show some complexity is that in these studies, for each mouse, about 20,000 cells were recorded using mesoscope resonance scanners, so they can image a big number of cells at the same time. So in a single session, you would record from 20,000 cells, and in a cubic millimeter, you would have access to about 100,000 unique cells. But so the volume would be bigger, but and over time, you would collect about 1 million neuron hours from each animal. And of course, one animal was pushed through the whole, through all the experiments, but many animals were imaged this way. And then combining multiple modalities, behavior simulation, stimulation, so visual stimulation in this case, there was a complex collection of stimuli with natural stimuli, static, and movies, as well as synthetic stimuli, parametric stimuli. And a lot of attention, and we'll talk about quality control. Quality control is something that everybody knows we need to do, but very few labs actually do it well. And so providing standardized tools for controlling the quality of the recordings with simple things like, the eye is closing in visual experiments, or tracking the brain state, like is the animal awake and attending. And then any sort of, in terms of imaging, any sort of interference with the optics, for example, or presence of movement. And one big problem or disconnect in neuroscience is that people who develop tools for data analysis, data acquisition, often do it in a sandbox environment where they just have a couple of data sets and they're playing with them and they're really optimizing the system. But in real life, running real experiments, a lot of things happen very differently. And if the method doesn't adapt to all the perturbations that happen in real life, then a lot of conclusions may be either misinterpreted or missed. And so another demand is efficiency. We need to be very efficient to be able to succeed in science. You cannot afford to spend a lot of time on data engineering, basically moving data around, copying data, carrying it, and doing this manually. So one example is this inception loop experiment where, due to automation, two teams were able to work on a single experiment, one in a very tight loop, where the results of analysis were used to drive the next day experiments. And flexibility. So there is a trend towards standardization, for example, in spike sorting or in segmentation of calcium imaging movies. A couple of tools in each modality have emerged kind of as the leaders, and a lot of people are using them. But at the same time, and some people believe that we're finally converging. We're almost there to have the standard tools where we can consider the problem solved and just move on to other things. But in reality, we continue to experiment, and I think my personal belief is that we will never converge. We will continue to improve and even maybe accelerate improving methods for spike sorting and segmentation, and there will never be a convergence to a completely standard final optimal way of doing things. So, and some signs of this are these competitions, for example, for the best calcium deconvolution method. So the problem is far from being solved. In spike sorting, the Spike Forest project by Jeremy Maglin is a benchmarking a resource for comparing new methods, and it reveals a fairly low correlation and a high sensitivity to the types of recordings that you're performing. So things will continue. So the key to this is to be flexible. A lot of labs get locked into a single method, and if another lab uses a different method, and they do not find different findings, it could be a reproducibility could suffer simply because the methods are not compatible. So something that we do with DataJoint is DataJoint workflows allow quick shifts and or simultaneous analysis, coexistence of multiple methods in the same workflow, so that you can track different methods. So flexibility is key. Another part that people are increasingly demanding and that projects rely on is data visualization, but nearly real time. So you basically want to have data, to have a quick view of the data and high quality visualization. So for example, the International Brain Lab, where data are from multiple sites are ingested, they have a shared web interface where you can get a quick glimpse of the current state of the training of mice, the quality of the recordings, and staying in close touch with all the phases of the analysis as you streamline the acquisition, streamline your experiments, but getting a quick look. And something very similar is done in a lot of leading labs, basically, where even though things are highly efficient and automated, you still have insight into the details and of the quality of the raw data, and so having these processes in place will be important for both efficiency and quality control. So the solution that we're working on, that we're providing, it has these three components: the DataJoint framework, which is not neuroscience specific, and it's very general, and it's for scientific workflows and databases. DataJoint elements are specific solutions within that framework for right now for neurophysiology. It can be for other things, but the funded project for the remaining 4 years of the grant, we plan to make this self-sustainable so that workflows will continue to be developed through community-driven developments, as well as through paid projects that we're serving. And DataJoint SciOps is meant to be a part of the sustainability roadmap. So we can deliver these solutions very efficiently, run them on scale as a team, and to provide them as a resource, as a tool to researchers. And then we can create a loop where new projects that develop new workflows working with us can contribute them to DataJoint elements, and so this can become a permanently sustainable ecosystem. So what are some upcoming developments for DataJoint? DataJoint is I would say, in its early phases of development. So we've been developing and continually using it for over a decade, but a lot of things will continue to develop. So workflow management is a new type of software, an emerging family of tools. Well, I would say over the last about 15 years, it's become a very major area of development across the sciences, and there's quite a few. I'll show some resources. So the experiment workflow and all the steps in the analysis, it's a valuable asset. It's an intellectual property itself that's worth sharing. Right now, there's not a really, it's like the closest equivalent is the methods section in your paper, but that only captures a few basic elements, and a detailed, a formal capture of the process that you use for data analysis. That really is not, other than DataJoint in neuroscience, is not currently very prominent. So this is what one problem we're addressing. So it's kind of missing in the field, and now that's why DataJoint is enjoying this quick, this sizable traction, because it provides a way to share workflows. So if you are a postdoc in the lab and you use it, then you can take that entire process and replicate it in a new lab, for example. And that includes all the processes, the automation, the scripts, and a way of integrating the team around shared workflows. One trend is for using advanced neurotechnologies. Basically, as new instruments come online, we need to be able to integrate them so smoothly. So as NeuroPixels 3.0 comes out, or a new scanning system, we would be able to quickly deploy it in many labs. Because right now it takes considerable time for labs to start using a new technology once it comes out. It requires infrastructure, it requires new tooling. So sometimes people have to hire an additional person to just implement the process. Another thing that needs to happen is managing the data consistently across the entire data lifecycle. There are many different cultures in science, and in many institutions, what we see is the data is managed, the data is not actively managed. And so what happens is each student, for example, graduate student, when they start their project, they kind of organize their data, they organize their code, and only they keep track of it. And then once they're done, nobody works with that data anymore. So establishing a common process will greatly accelerate. This is something that a good workflow management system can help accomplish. And another thing that we need to make easy is access to high performance computing. So right now it takes quite a bit of skill to be able to deploy your computations on a cluster or on a Hadoop type of system, so that for big data, for high performance computing, it takes quite a bit of skill. If we provide a framework that lets you debug something on your laptop, and then once you are ready to go big, it doesn't take a lot of retooling, that's something we want to accomplish. And so that's what the DataJoint provides. You can start on your laptop, debug it, and then deploy on a big system with distributed computing without a lot of change. So these are some goals that we're trying to accomplish. And so in solving these, we saw this slide yesterday. Basically, we need to solve multiple layers. And so if we can address the low level, the information technology and the data engineering operations, and allow people to focus on the data science and experiment workflow, we will greatly accelerate and improve how the field works with big data and computations. So these are some new upcoming framework capabilities. And this talks about specifically DataJoint, but also the ecosystems of tools around it. First of all, we need to continue to shore up the open source foundation, basically, to run the project with the best practices in transparency, responsiveness, community involvement, and clear governance, so that DataJoint can be relied on as part of the digital infrastructure, basically similar to other tools, like, it's open source tools that everybody uses. So this is something we will greatly emphasize. We need new capabilities for data export, save, and restore. So right now, DataJoint really is used as a workflow tool, but increasingly people need to export the data for use in other tools, and it can be done right now, but it's pretty difficult. It takes extra steps. So we want to add these capabilities to automate and streamline this process, including for exporting into NWB, for example, Neurodata Without Borders. So DataJoint has a native way of implementing standardized way of computing. So with the make method and the populate method to streamline and distribute the computations. We are working on a similar solution for native support for visualization, scientific visualization, so that every entity in the workflow knows how to visualize itself, and then a standard web interface for data visualization and navigation can use these features to streamline the way how you create a website for navigating and reviewing the data. Finally, so workflows are really meant to be deployed automatically, and they need to know how to set up the environment and infrastructure, computational infrastructure. So right now it's done separately and manually, and that requires additional work. So if we will be working on adding these capabilities as a native component, as an integral component of the DataJoint framework, so that we can automate the definition, the configuration of the computational infrastructure and all the dependencies. Actually, I had a figure here. For some reason, it's not showing, but you can go to neurocast.org. I wonder why it's not showing. So Neurocast is a project at Columbia University and we are working with John Cunningham, who's running this project. Neurocast is basically a neuroinformatics as basically architecture as script. So it's a separate project. It's not integrated with DataJoint, but we are working together on finding solutions to basically simplify how cloud computing and other basically scalable architectures can be deployed. So the aim is to allow for each workflow that you specify to track the code, so that you always know with what code everything was analyzed, with all the dependencies, all the libraries that were used, and the computational infrastructure to enable automated deployment either through our managed services or independently. So one of the principles that we want to implement is that even though we as a company provide efficient and convenient services to operate the workflows, they should be completely reproducible and open, so that if you need to reproduce it on your own infrastructure, you can always do it. So DataJoint, of course, is one of many workflow management systems. And there are so many of them. You will look at, there's this list, an incomplete list of workflow systems. And number 256 on this list is DataJoint, but there are so many, basically hundreds of other workflow management systems. It's a really exploding field, and there's not a really clear leader or clear approach. Most of these methods use command line utilities. And of course, we try to integrate a lot of tools that are command line utilities, but in many cases, there are some just Python code that we put in the make method. A lot of these methods, they allow configuring the data sources, but what makes DataJoint unique among all these systems that it combines, it creates a database as part of its, a structured database as part of its operation. In fact, most of the workflow systems, they're really code focused, whereas DataJoint is data focused. It's data centric. You create a database with computational dependencies, and the sequence of operations and the sequence of analysis determined by the structure of the data. Whereas in all the other workflow management systems, it's the other way around. You specify the sequence of processing, and and the data is organized to accommodate that processing. So even though DataJoint fits the description of a workflow management system, it takes a completely different approach and accomplishes different aims. But these methods are so diverse that there has been a need for developing a common workflow language. And so you can go to commonwl.org. And this is an open standard effort to introduce some order to the chaos and introduce a common language among all the workflow management systems. We're not yet supporting the common workflow language, but it's a important trend to be watching, because in other fields, this is a really great video. I'm not going to play it right now, but the first 40 seconds, and you can access it by going to this website, or just going to the commonwl.org. And basically, across all fields, there is a need for automating standard repetitive tasks, so that combine many different steps. And especially in dynamic environments such as science, where you cannot really just figure out your workflow and just optimize it and leave it alone, where you're constantly tweaking things, optimizing things. That's where workflow management systems become necessary. So it's
in many scientific fields such as bioinformatics.
So you can use this. All right. So for all workflows, increasingly and for always, we need a graphical user interface. So workflow DataJoint does not by itself provide a graphical user interface, and there have been many different systems and approaches to do this. And the one that we provide as part of the elements is the combination of FAIRS, which is a REST API to allow multiple different types of web-based interfaces, and DataJoint Labbook, which is a front end. So you can set it up, and there have been some precursor projects such as Alex from Cortex Lab and Helium from Janelia. So we have used them as web interfaces that feed data into DataJoint workflows. So one important development this year will be simplifying the export of all data into the NeuroData Without Borders format for data sharing and dissemination. So DataJoint itself will provide a method for exporting the data more generally, so that it can be shared in different formats, in HDF5 in particular, more generally beyond, that is not just what fits the domain of NeuroData Without Borders, but for general schema. But for NeuroData Without Borders, for existing workflows, will provide this functionality. So if you use one of the existing elements for, say, electrophysiology analysis, and you need to publish the data in a given format or submit it for archival, you can do it with in a much more streamlined way. Right now, when we've done this a few times, it takes considerable work to package data for publication and dissemination. So another effort, and this is taken from dandyarchive.org. So Dandy Archive is an NIH-sponsored distributed archiving system for what they call Dandy sets. Some of them, or most of them right now, are based on the NWB format. But also the intention there, this is their proposed architecture, is to enable interactive collaborative work online with these data sets. So once they have been published, people can use Jupyter Hub or collaborative environments where they can analyze jointly and share results. And so we are working with the Dandy archive team to provide integration where pushing the data from DataJoint workflows directly into Dandy Archive will be automated. So DataJoint Elements is a 5-year project. The specific aims to provide to systematize essential motifs, design motifs existing projects. So we're not necessarily developing all the modalities from scratch. We're always working with some precursor projects that use DataJoint for each modality of neuroscience. And so the idea is to cover all the major modalities of neuroscience, depending on how you define this. But in the initial proposal, we focused on these, the ones that are listed on the screen. But neuroscience is a highly dynamic field, so we need to adapt as new modalities emerge and as new projects become prominent. And then another specific aim is to provide all the training infrastructure and environments for development in all the guidelines. And so this activity here is part of this specific aim. The scientific steering group comprises some leading researchers across all the modalities or all the major modalities of neurophysiology, including computational components. And so they provide guidance in the selection of project components. So a DataJoint element is a technical term that we design. Is basically a module. So we design workflows in such a way that that a workflow can be designed from pieces, from elements, to accommodate very diverse experiments as you combine multimodal. You build your multimodal experiment. And they're designed for simplicity, for integrating, and they also come with integrations into any interfaces, such as graphical user interfaces or ingestion scripts from common acquisition systems, so that we can work with different varieties of instrumentation, as well as exporting. All right, so something that we're still working on is tracking their usage and also identifying the version. So there is an RRID, or research identifier, so that all the versions and everything can be clearly identified and citable. So that will be coming out this year as well. So we establish a resource management plan how we make decisions. And this is basically, people are free to propose and pitch what needs to be included in the elements and offer to the community. We engage in outreach, where we try to find at least 3 precursor projects for each modality. So say if we provide an optogenetics element, we will work with a couple of groups that use optogenetics, especially if they use DataJoint with their optogenetics pipeline. And we engage with them to interview them, to understand their process, to review their code, what all the tools that they use, all the steps. And we also ask them for sample data, so that it can be used for our own validation, but also for training, so we can provide it to others. And once we implement, we have an excellent software team that follows a quality assurance process, where we follow coding standards. We automate all the testing, so that any changes will go through regression testing and integration testing. And we work with external contributors, because basically DataJoint combines the tools developed by other teams, by tool developers across the field. And so we work directly with teams. So if somebody's developing, most people are developing tools for a specific task, for segmentation or for spike sorting, and we're integrating the entire process. We engage teams in new labs in validation. So for each element, we reach out to labs that do not yet use DataJoint, and we want to work with them to test it, how it works for them. During that time, we provide fully managed cloud infrastructure, so that they can quickly try it, see how it works for them, and then they can decide whether to replicate the setup in their lab, or use the cloud service, continue to use the cloud service. So they can transition to self-management, or transition to a contract with us to continue to support their project. And we are building in the infrastructure for feedback. INCF is a great resource for that, and we will use some of the some of the resources that for collecting community feedback and discussions, setting up work groups, but also all the software comes with issue trackers, so we can be quickly responsive to all the changes, to all the issues. And for sustainability, so when we take on a project, we make sure that there is at least roughly at least 100 labs that are in need of something like that. So we're not developing for a small group of labs. So, and we work with all the developers to make sure that the tools that are developing have a sustainability roadmap, so that we will know how long, if they have funding, how long they're going to support, so that, for example, if they're no longer supporting a tool, we want people to know, okay, this tool will probably not be supported, and so we recommend other tools to replace it. And so all the components of DataJoint workflow have predictability about how long they will be around, so you can make choices intelligently for long-term continuation and sustainability of your own project. And so we're trying to so we work with a lot of labs to adopt and to test. We create dissemination resources, websites, conferences, workshops, as well as online tools. I don't know what happened here. Sometimes Google Slides gives these. Okay, so a big topic is quality control. So this is something that a few labs have developed for themselves. And we definitely need to propagate this, and I will illustrate this. So quality control is often omitted, and I myself, during my graduate school, I lost many months of experiments because of a missed optical problem. And this just shows the effect of calibration in calcium imaging, and it's performed regularly, but not regularly enough, and a lot of labs don't have a procedure for that. These are point spread functions. These are basically beads imaged in a 2-photon calcium imaging system, and depending on how well it fills the backfocal aperture of the objective lens, it might look something like this. So each point you can see kind of smeared, and this is very common, and it's hard to catch if you don't test for it. And so by just adjusting, so this is the difference, by just making sure that the laser is aligned and fully fills the backfocal aperture, the size of and you can see that especially in Z, the point spread function in the axial direction of the objective, it can get pretty long. So even in a well-focused system, it can be pretty wide, several microns. But if it's not calibrated, it can be 10 microns and more. And so that means that when you're imaging, even though the cell appears sharp, because in X and Y, the resolution is high, so the cell body in the image looks pretty sharp, but most of the signal comes from above and below the cell, or from neuropil, and so the signal is highly contaminated. And I myself lost a lot of time. It was, in my case, there was a warped mirror, and the problem was a lot worse than this, and no calibration could help, but the problem went undetected for several months. And so for microns, because it was a very high value project, there were a lot of quality procedures set in place. So there was since there was a lot of cost, so initially calcium imaging was performed, and then electron microscopy and then dense reconstructions. This involved tens of millions of dollars in terms of, if you mess up your image quality in the beginning, then all the subsequent analysis and experiments are reduced in value. So there were so this is the imaging, how it was set up. And the stimuli that were presented, some natural stimuli and synthetic stimuli. And then metrics of image quality were set up so that we could regularly monitor across multiple animals how the system was performing. And so these were streaming. So DataJoint was used to automate both the data acquisition or the data analysis and the quality control. And these were streamed into a Slack channel so that everybody could review them on a regular basis. So as pre-processing was performed, motion correction, everything was aligned. So a stack was acquired of 30 microns deep around the imaging site. So one interesting thing that happened as part of this, as you acquire the stack, you can correlate each scan to its position in the stack, and you can know the motion both in X, Y, which is typically done, but also in Z. And what was discovered is that there was a lot of drift. You can see here a lot of drift occurred by several microns in Z. And you don't see this by eye, and motion, just planar motion correction does not catch that because it's movement in Z. But what happened was, because the room was air conditioned by an air conditioner that was across the entire lab or the entire floor, I'm not sure, that variations in the temperatures, the air conditioning turned on or off, caused various forms of thermal expansion in the setup, and that introduced that drift. And so basically every several minutes, there was motion in Z. And after fixing, basically introducing temperature control right in the room where that was just the air surrounding the setup, that motion, that drift completely went away. So these are subtle things that you may not be aware and not catch for many years, and basically lose a tremendous amount of value in the data by just not tracking simple things like the presence of thermal drift because of the air conditioning system. So in the lab, so this is behind a firewall, so you need VPN to access. There was a system set up, and I can go there and show some of these quality control checks that were performed, if we have time. And basically, for each experiment in real time, as the data gets analyzed, you get, actually, I think we'll skip it this time, but you get a measure of how good the data is. Actually, we have a few minutes, so let me just quickly show this. And we'll use this mouse. So if we go into quality control, and for a specific mouse that I selected here, so this mouse, and then the connection is 96, or the scan number, session number, and the scan number. So as you see, basically the quality of the data for each scan, so this appears automatically. So a lot of labs would benefit from a process where you can get a quick view of the quality metrics for all the scans, including things like how the contrast changes. So a change in the contrast indicates that something happened optically, sometimes water escapes. So these are trivial things, but basically, but introducing these common checks across the field will make it a big difference. So our focus, so one of our thrusts for DataJoint elements would be to add quality metrics to data across most modalities, including electrophysiology. All right. Let me go back to presentation mode. Okay. So, for example, just for QA, for the calcium imaging, we need to track the calibration, how the power of the laser going in. So these are the parameters that we need to track. But the brain state, even keeping track of whether the mouse is awake, if its eyes are open, and then all the artifacts of scanning artifacts, correlations between frames, which basically means something happened. So if the last frame of the movie does not correlate to the first frame in the movie, something happened. And so a lot of these checks need to be performed for you to make sense of the data. Okay, so SciOps is our managed solution. So what we found when we first started working, just giving DataJoint to everybody is just, people need a lot more than just access to the software, because teams need to organize, they need to plan, they need to write grants. And so we identify these 4 areas where we can help, is to create plans, to define the workflows for specific experiments, then to host and operate the workflows, because sometimes it takes an additional team member to enable this. And then collaborate and publish, how to share the data efficiently, give access to your collaborators. So for data science and publishing, you can work with us and basically mostly do everything yourself. Everything is accessible. We try to document everything in a lot of detail, or you can scale it up to a fully managed cloud-based solution where we take over the operations. But in either case, the level of integrity, data integrity and transparency is the same. You have access to every step, every transformation, all the code that it applies to your data. And many other activities, like especially as you propose to advance the field and introduce new methods. So defining how you will manage the data and computations, it becomes critical. And then setting up the resource management, computing resource management, especially in collaborative projects, it needs to be done well. And setting up basic good practices like code management and provenance of the data are essential. So workflow definition, in most cases, we already have something that's available for many modalities of neuroscience, especially if DataJoint elements progresses. But for many cases, you have to develop new workflows. So this includes defining how the data is entered, what systems you use, what formats for the acquisition, how data are synchronized between the different modalities, what formats it comes in, what analysis steps, how they need to be automated. And you can start with something that already works and then customize. So something in neuroscience, unlike other fields, standardization is more difficult. It's more challenging. It's not like in bioinformatics, which genotyping can standardize because it's much simpler, effectively much simpler modality. In neuroscience, we will continue to have very diverse solutions. So standard workflows can be, if the solution that you're developing is applicable to many labs, we can adopt it into the DataJoint Elements program and basically use this funding to further develop it and disseminate it. Yeah, so our team can work with you to develop these. And then hosting and operations, basically, this is once you develop the workflow, just automating it and keeping all the systems monitoring, basically automating and configuring, automating, procuring, if you're running in the cloud or if you're working with an IT department. Sometimes communications with the IT department can take a bit of work. So if you clearly communicate what you need, it becomes much simpler. And then give them instructions on how to automate so that the data, as soon as the new data appears, it's pushed through the pipeline and you have access to the results of processing and analysis. Especially if you have manual steps like curation involved, there are a lot of moving parts. So and in a lot of cases, you work with others who want to have data access to the data right away. So that can be set up, and there are standard processes. So we work with teams to create that common access. You can decide who has access to what, or if it's more of downstream, more for publishing, there are standard interfaces for exporting and submitting data for publication. And so with this, we provide engineering support to adopt the workflows. So this basically means that with the DataJoint Elements funding, we can, if you're adopting one of them in your lab, we can provide you with help as part of this funded project. So you can apply there. So another program we're doing is setting up some of the projects that use DataJoint. There are many now. We take their data and put it online for exploration and also for learning, for tutorials. We just started with microns, but we're preparing many more. So that's something we'll be announcing at SFN. Basically, lots of data sets, big, interesting data sets that you can interact with without setting anything up through just the web browser. And if you know DataJoint, you can write your custom scripts, custom analysis, and get some really cool results. With things like microns, we haven't even begun exploring it in terms of all the findings. The data are so rich that we'll be able to find lots and lots of new discoveries. Okay, this is our team. Again, I'd like to thank the entire team and also all our collaborators. There are many of them. And this is just the team and our scientific steering group. All right, thank you very much. And we will continue at 11 o'clock Central Time, so in 9 minutes, with the actual hands-on tutorial. I hope this provides you with some view of what's to come. And if there are any questions, please let me know. Any questions? All right, I'm stopping sharing. All right. All right, thanks everyone. And we'll see you in a few minutes for the hands-on tutorial.
All right, good morning, everyone. Morning, everyone. Thank you, Dimitri. That was an amazing presentation. As you said, we'll be starting at 11 a.m. Central Time. So if you're new here, I just put the link for the workshop in the chat. And if you were here yesterday, then we're going to be navigating back to the same link. So we have about 7 minutes. And so we'll be starting then in about 7 minutes. If you have any questions, feel free to ask in the chat. Thank you. All right. Good morning, everyone. Welcome back to day 2 of our presentation. For those of you who are new, who weren't here yesterday, my name is David Godinez, and I am a data engineer here at DataJoint. And so yesterday we had a great time going through the basics. And so today we'll continue, but not the fundamentals of the DataJoint framework. And so what we're going to do today is that we're going to have a short review of yesterday for the people who weren't here. And even for the ones who were here, we'll just do a quick recap, and then we'll move on into deeper concepts, fundamental concepts here at DataJoint. So I'm gonna share my screen once again. I posted the link to the workshop, so it's in the chat. INCF 2021.datajoint.io. If you have any concerns, any issues, anything that needs to be troubleshooted, please feel free to let us know in the chat. So I'm going to share my screen. All right. Awesome. And please let me know if you're seeing my screen. It should just be the folder directory, the workshop directory. Thank you. Thank you, Tim. Thank you, Julian. Welcome back. John, welcome back. Awesome to see you guys back. It's a pleasure. And yeah, so again, for the people who weren't here yesterday, and for the ones who were, we'll do a quick recap. So we went through notebooks 0 and 1 yesterday. And notebook 0, we learned how to import DataJoint. We learned about the dj.config attribute. And so we import it. We learned that this config attribute tells us quite a bit of important information. But for our purposes right now, the primary 3 bits of information are the database host, database user, and database password. And so we learned how to configure that using the syntax, right? So you do dj.config, and you let DataJoint know. You say, hey, DataJoint, this is my username. And you say, hey, DataJoint, this is my password. And then you use dj.con to test your connection, right? This is another way of configuring your username and password. So you could type in dj.con and it's immediately going to prompt you to do it. So yesterday we didn't see this. And after I finished the presentation, I was like, today I told myself that I would show you guys this one today. So you put in your username, David Godinez, and we see that we're successful. It says connected. So David Godinez is connected to tutorial-tb.datajoint.io. So that's our database as defined up here. So now we have 2 ways to configure that. We also learned how to save our configurations locally using the dj.config.saveLocal method. And then we went into dj.config.saveGlobal. So of course, that's saving your configurations globally. And finally, we learned if we so desire, if we want to change our password, we can do datajoint.setPassword. All right. And if you do change your password, then you would have to change your password in the dj.config file as well. using the dj.config method. All right, and so that was getting set up with DataJoint. Did we have any questions there? I want to say that part was pretty straightforward. But I think we're okay. All right, and then we went into notebook 1. And so this is where we really begun to get our hands dirty. And so we imported DataJoint. We spoke about what a pipeline is. We explained, one of the first things we explained was that, we use pipeline and workflow pretty interchangeable. And we explained that a pipeline is the sequence of steps, more generally a directed acyclic graph with integrated storage at each step. And these steps may be thought of as nodes in a graph. Right, and so, we further went into detail about these nodes. We spoke about how if constructed well, a data pipeline could give you further insights into the connections in your experiment. And we explained that, your data pipeline shows you the things or the nouns in your experiment and how they relate or their relationships to each other. And yesterday I read something, and I want to go over it. Yes, John. So John has a question. So I have a question. Right now, the database hosts in tutorial, but if I want to make a real implementation, what would the host be? That's a great question. So there's a couple ways you could go about that. So if you do it on your local machine, then you would have a database set up on your local machine, such as some type of MySQL database or MariaDB. And so from there, you use what's called your local host. And you let DataJoint know that in your config file. If you're in a lab, and then they're going to have their database, and you connect to that database. All right. And so yesterday I read this part about building our first pipeline, and not trivial. So localhost, your local host is trivial enough. It's the simplest way of, as long as you install MariaDB or MySQL or some type of database, you should be okay.
So maybe, David, I can add a little bit to that.
Yeah, please go ahead.
Yes. So indeed, as David said, right, you would have to, John, essentially, you would have to point yourself or DataJoint to a database server somewhere, right? That either be it on your local machine if you install things yourself, or if your institution IT has a dedicated database server that you can connect to, that's also another way. But yes, you indeed, that's not trivial, because now you have to kind of manage the database yourself, right? Or if you're doing that locally, you have to make sure that you're doing the job of a database admin, which depends on your study. It can ranging from fairly straightforward to some sort of nightmare. Right. That's what we've gone through. So yeah. So but you're welcome to continue using the tutorial database for your test out, kind of like a scratch pad, something like that. It's really not meant to be like a scale up performance. For that, on our DataJoint, we do have a kind of like a hosting service. So maybe David will go through it later, or I can go through it tomorrow, where you can use DataJoint SIOP service that would provide fully managed database server and also operating your data pipeline for you as well. Right.
Thank you so much, Tin. And if you read in the chat, our CEO Dimitri just placed the link to our DataJoint SIOPs page. And so, as he said, our managed service, DataJoint PsyOps, provides fully managed infrastructure to support real experiments and studies. So thank you, Dimitri. And Kabilar also said, as a related aside, we will be discussing setting up a local DataJoint development environment on the Thursday session. Yes. So on Thursday, yes, that's a great point. On Thursday, Kabi will be showing us how to get set up locally. So you don't want to miss it. Right. That's an excellent point, John. And that was one of the reasons we decided that Thursday would be to showcase how to really get set up on your local environment. So thank you for bringing that up. So what I'm gonna do right now is I'm gonna reread All right, so we're getting an error message for Julian. Using password, yes. Yeah, the password is not. Maybe you can try it again, Julian. All right. Let me see. Should we what are we thinking, guys? Could we do the check your database host? Yes. So let me go back. So your database host ideally would be tutorial-db.datajoint.io. All right, thank you so much, Kabilar. All right, so Julian, for right now, please sit tight. And we have a great team over here, so we'll get it taken care of. So in the meantime, we're going to continue with building our first pipeline. Thank you. Yes, we're going to go ahead with building our first pipeline. And as I said yesterday, as we move on, we'll be focusing on the electrophysiology section. But please feel free to come back after our sessions. And you can see here that we have an electrophysiology session, but we also have a calcium imaging section as well. And so you can go through that on your own. It's great for learning. It's great to sharpen up your skills. So please feel free to use the resources. That's what they're there for. But for the purposes of this workshop, we'll be focusing on electrophysiology. So I'll just reread this part right here. It says, your lab houses many mice, and each mouse is identified by a unique ID. You also want to keep track of information about each mouse, such as their date of birth and gender. So we remember making that mouse table yesterday. As a hardworking neuroscientist, you perform experiments every day, sometimes working with more than one mouse in a day. However, on any given day, a mouse undergoes at most one recording session. So we'll recall that because a mouse could only undergo their session one, each day had to be unique for the session. We were able to use that as a part of our primary key. And finally, for each experimental session, you would like to record what mouse you worked with and when you performed the experiment. You would also like to keep track of other helpful information, such as the experimental setup you worked on. Excellent. So those are our mouse and session tables, right? Now, in electrophysiology, you record the electrical activity from a single neuron. And you use recording equipment that produces separate data files for each neuron that you recorded. The neuron's activities are recorded as raw traces, and the neuron spikes need to be detected for further analysis to be performed. Excellent. So just as a quick reminder, we define our, let me import DataJoint here really quickly. So just as a quick reminder, all your tables sit inside schemas. So you always have to define your schema. And I'm just gonna put this in once more. Oh, let me see. Oh, sorry. So that's my mistake. All right, let me restart this real quick. All right. Yes. Let me see. Oh, I'm sorry. Typo. Sorry about that, you guys. Do this once more. Now we should get it right. All right. So now we have our schema. And now that we have our schema, of course, we are going to populate this. We're going to put in our tables. So our first table was the mouse table, which we defined. And remember, when you want to run a table, you do, you call the name of the table with the two, with our parentheses. To insert, we have our insert one method, and you could insert using tuples. You could also insert using dictionaries. Thank you, Kabi. So Julian, maybe you can check your username. Right, and we could also, all right, awesome, thank you. Thank you, Kabi. And so there were, we worked on different ways in which we could insert data. So we could insert it using the insert one method, and we insert data one row at a time or one instance at a time. We could insert a list of tuples or a list of dictionaries using the insert method. And we said that one very important concept of DataJoint and one of its strengths is that it enforces data integrity. So you can insert, that was it. All right, I'm glad you got in, thank you. As I said, we have an amazing team on our side, so we're always here to help. So DataJoint enforces data integrity. So if you try to insert duplicates, it's gonna let you know, hey, unless you use that skip duplicate argument. Going down the line, we learned about tables with dependencies, and we spoke about the fact that DataJoint is built on the relational model that framework, meaning that tables downstream are dependent and they're related to the tables upstream. So we defined the session table, and we said that there are two ways to look at this diagram. You can use the ERD syntax, or you can use the diagram syntax. Right, and so we see our beautiful pipeline forming once more. And, oh, well, that one, these are all already inserted, but yes. And then we learned about querying the data. And so we said, once you have the data in these tables, you might not want to work with all the data at the same time. And usually the case is that you only want to work with a subset of data. And so we have different types of queries to help you retrieve a subset of that data. So we have the restrictions, and we learned about our ampersand, right? And we saw how powerful that was. You could use equalities, such as this one. You could use inequalities. You could look for a range. You could use not equal to, right? So inequalities. And you could, yeah, you could even combine. So for example, if you wanted to look for all the mice that were not male, whose date of birth was after a certain date, you could do that as well. So it's a very powerful, and I can't stress this enough, intuitive syntax. So we could combine restrictions. So you could restrict using tables. So you could say, I want to see all the mice that have a session. You could combine these. So mice with a session who are male. Or here, mice with a session whose session date was before or equal to the 19th of May. And then we learned about the negative restrictor. So this is telling me, or this is telling DataJoint, DataJoint, show me all the mice who do not have a session. So the restriction queries are extremely powerful. Then we learned about the join, and we learned that the join we learned that its behavior is to match the common fields of primary keys in the two tables. And we learned that what it does is that it creates a combination of the non-matched part of the primary key, and it lists out the secondary attributes for each combination. And we said as a caveat that if your secondary attributes share the same name, so if you have two tables that you're joining and both tables have secondary attributes with the same name, DataJoint will throw an error. So you would need to rename at least one of those attributes. So we looked at joining, and we could see that we have all our fields from both tables. And so we could join and use our restrictions, join based on restrictions. So in this case, we're joining the mouse and the session table, where we're restricting our results with our experiment being Jacob, and only on male mice. So we got one result there. So that was the join. And then we learned about the proj, which is another incredibly powerful type of query, where what proj does is that it allows you to select specific attributes from a table. It allows you to rename these columns or these attributes. And it also allows you to create new columns or new attributes, which are derived or they're calculated. So for example, if we just wanted to, we recall that mouse had 3 columns, right? Mouse ID, date of birth, and sex. If we say, hey, DataJoint, show me only the sex column. So the way we do it is we say mouse.proj, and we specify sex. And so we get our primary key. In this case, it's just one primary attribute, mouse ID, and we get our sex, which is what we wanted to see. So renaming with proj, we call our table name .proj, and inside the brackets, we put the name that we want the column to be named, and we have our equal sign, and we put the column that we're renaming. So in this case, we're renaming the DOB column to date of birth. Excellent. We saw again that we could perform computations with proj, which you can just imagine how powerful that could be. So here we want to combine or join the mouse and the session table, and we want to create a new column called age. And the way we create age is we use a dated diff for session date and date of birth. And we said that whenever you create your new column, if you only specify the column that you want to create, that's the only secondary attribute that's going to come up. If you want to see all the secondary attributes, you can use the ellipsis. And there we go. So we have our calculated column, age, and we have all our other secondary columns, as well as our primary key or primary attributes. And we were very sure to say that while querying is extremely powerful, querying is really, we use the analogy of going to a bakery and looking through the glass and you see a piece of cake, right? You tell your mind, hey, I want to find all the pieces of chocolate cheesecake that are in there. So you look, you see a slice, but so once you found what it is that you're looking for, once you found your subset of data, then you want to download it to your local machine and you want to use it. And to do that, we use the fetch method. And so we said first and foremost that fetch returns your data as an array for the most part, right? Unless you're getting the key where you'll get a dictionary. And so there are several ways to do a fetch. So in this cell, what we did was define a variable and we used a query. And then we called fetch on that variable. Another way to do it is a bit more direct way, is you just call fetch on the query itself. And we saw that fetch has quite a bit of arguments that you could put in there. So you might want to fetch your data as a dictionary. You might want to fetch, for pandas lovers out there, you might want to fetch it as a data frame. And you could even fetch specific parts of your query, right? So for example, if we wanted to get all the mice who were male, but we only wanted the primary key, we could tell DataJoint as its argument in here that we only want the key. And so we get the keys of all male mice. We saw that we could, yes, fetching specific key, fields. Yes. Excellent. And we saw that in the same way that DataJoint has the insert and insert one method, we also have the fetch and the fetch one method. And so you might want to use the fetch one method when you know that there's only one result to be gotten. So for example, in this case, we only want to get the result for mouse 0. So there's only one mouse 0. So we could call a fetch one. And there we get a dictionary with this information. And again, fetch one uses, you could also, it has pretty much all the same arguments as fetch, but of course you get one result. And then finally, we saw the delete method. And so you could run a query, much like in fetch, you run a query and then you call the delete method. All right. And yes. And so DataJoint, if you have an unrestricted, if you call the delete on an unrestricted table, so meaning that you don't specify what it is that you want to delete, DataJoint will be sure to ask you, well, first it'll be sure to tell you, hey, so if you call this delete, you're going to be deleting rows from, it'll tell you all the tables and their dependencies, where you're deleting data from, and it'll ask you, are you sure? So in this case, we'll say no. So it says delete's canceled. So awesome. So we covered all of that yesterday. Do we have any questions before we move on? All right. So I think we got it down. And so today, we get into imported tables. So yesterday, we saw that as we were defining tables, that next to the class name, we put in the argument dj.manual. And so we were telling DataJoint that the data that goes into this table or into these tables, we're going to be manually putting them in. So today we'll be talking about a different type of table, or two different types of tables, the imported and the computed tables. They're similar enough, but so we'll be talking about them. And so officially in this session, we'll learn to import neuron activity from the data files into an imported table, and we'll automatically trigger computations from all missing entries with populate. So, and this is, I'm just gonna go back here very quickly so that we understand exactly where it is that we are in our overall objectives. So we've done everything that we said we were going to do up here. And so now we're going to create tables to store the recorded electrical activity from our neuron. And then we're going to look at those recorded as those raw traces, and we're going to extract the spikes. Excellent. So of course, we import DataJoint. And we're also going to import NumPy as NP. And we're going to import matplotlib.pyplot as PLT. For people who have, for those of you who have been in the field of data science, or if you're an avid Python user, specifically for data or scientific experiments, you're familiar with NumPy and matplotlib. So those are going to help us with our calculations and visualizations. So now we would like to continue working with the tables we defined in the previous notebook, right? So the mouse and session. To do so, we would need the classes for each table, mouse and session. So we can either redefine it here, but for your convenience, we've included the schema, so schema, and table class definitions in a package called tutorial pipeline.mouse session, from which you can import the classes as well as the schema object. We'll use the schema object again to define more tables. So rather than redefine those tables, we'll import them from our package. So we run this cell. And yes. All right, so there we go. Excellent. So we have our mouse table with all its data, and we have our session table with all its data. So the mouse session.py package also fills each table with data to make sure that we're all on the same page. So yesterday we had quite a bit of time to insert our own data. We could, play around with it, delete data, and we could do things as we pleased. So using this package, it puts us all on the same page. So we should all be seeing the same things. Let me know if anyone is seeing anything differently, but it should be the same. So recall from the project description that in each experimental session, you recorded electrical activity from a single neuron. You use recording equipment that produces separate data files for each neuron you recorded. Our recording equipment produces a data file, yes, for each neuron recorded. And since we record one neuron per session, there should be one file for each session. In the data directory, you will find a .npy file, NumPy, right? A NumPy file with names like data 100 2017 525.npy. And as you might have guessed, these are the data for the recording sessions in the session table. And each each file is named according to the mouse ID and session date. So we could see that here we have the mouse ID and here we have the session date. So that's the convention that we're using to name the files. The attributes of the primary keys in the format data, mouse ID, session date. And for, as I'm sure we're all pretty curious, if you want to look for it, if you go in the electrophysiology pipeline directory, you see a folder called data, and this is where we have all our data. Yes, so data 100, data underscore 100 underscore 2017 0525 is the data for the session identified by mouse ID 100 and the session date 2017 of the 25th of May. So looking at the data, so now let's look at the data, okay? So we'll take a quick peek at the data file content. So if you remember, we use the fetch method to download this data, okay? So we'll get all the keys from all the entries in our session table, and we'll assign it to this variable called keys. So if you recall, or you don't have to recall, you can scroll up here. Session has these two primary attributes which make up its primary key, mouse ID and session date. So when we pulled the key, we get mouse ID and session date. So any item in the list of keys can be used to uniquely identify a single session. So what I want you guys to do is to restrict session. And this is a bit of practice for you. I want you to restrict session using keys and any element inside of keys. So you have 1, 2, 3, 4 different elements inside of keys. So I want you to restrict session with any element inside of keys. So it can be element 0, element 1, element 2, element 3, element 4. And I'll give you guys a few seconds to do so. As we did yesterday, you can type your query in the chat and we'll run it up here to see your results. Yes, I'll give you a minute. So this is just a bit of practice for you to, for like a restriction for you to query. And so if you recall, we're restricting the session table, right? So that's going to go first. And we're just using one element from keys. Does anyone have any ideas on how to go about this? We have about 20 seconds. All right, we're at about 10 seconds. All right, so I'm gonna help us out here. And so the way we would do this is we call it our session table. And we're restricting by keys, but we only want one element. So I might use key 0, the first key. And there we go. So this is how you restrict session by keys, by one element inside of keys. So let's take the first key and generate a file name that corresponds to this session. So remember that the convention is data underscore mouse ID underscore session date dot npy. So we're gonna create a template. And so we call for our key, we're going to use key 0. You could have used key 1, key 0, 1, 2, 3, or 4. And then we're going to have this variable called file name. And file name is going to be this string, okay? But we're going to do something really cool where we format the string using key. And so we're telling Python, hey, Python, I want my file name to have this format, right? And I want you to populate the data in mouse ID and session date from the data that we got in key. So we run that and we see that our new string is data/data_0. So meaning that we're using mouse ID 0, and we're using this date as the session date. So we've made use of Python's dictionary unpacking and format method on strings to generate the file name from the key. So now that we have the file name, we're gonna use NumPy to load it in this variable called data. And so let's look at this content. Beautiful. So we have a beautiful 2-dimensional array. And so this is all the data from one of the files that was in that data directory. Now let's go ahead and check the shape of this data. And we see that, so we see 2 square brackets here. So we know it's a 2-dimensional array. And we see that it is a 1, the shape of it is a 1 by 1,000. So this tells us that you have the raw electrical activity of 1 neuron. And it says this represents a simulated recording of raw electric activity from a neuron over 1,000 time bins, okay? Yes. So what we want to do now is we want to create a table that can import all this data and store it for us. Remember that a part of the definition of a workflow or a pipeline is that there's integrated storage at each step. So we want to integrate all our session data in a table. And since we're getting the data since it's the neuronal data, we'll call the table neuron. And if we recall, or as we recall, we tell DataJoint where we want this table to be. In this case, it's going to be in the schema. And we define the table roughly the same way, right? So we have our arrow and session, and we're telling it that this neuron table is dependent on session. So we know that session is dependent on mouse. And so neuron is dependent on session. And we have another primary attribute up here, which is neuron ID, and that's going to be an integer. And for our secondary attribute, we have activity, which is a long blob. And a long blob is a data type that can accommodate NumPy arrays. And for our eagle-eyed users, you'll notice that I skipped over this part. I left it last intentionally. So in our first 2 tables that we defined, mouse and session, those were dj.manual, but now we're using dj.imported, which means we're telling DataJoint that this table is going to get its data automatically. It's going to import its data. We don't have to put data in, manually. So let's check our schema. Oh, let me define the table first. Let's check our schema. Excellent. And so we see that we're going downstream, and we see our mouse table, our session table, and our neuron table. And as a quick note, as I said yesterday, one of my favorite things about DataJoint is that it is very visual. And so whenever you call on the diagram, you get not only the structure of your pipeline, but if you hover over it, you get all the columns that are in that specific table. It tells you what it's dependent on. So we see the arrow mouse, telling us that sessions dependent on mouse. It tells us the primary keys or the primary attributes, and it tells us the secondary attributes. And the final observation you'll notice is that mouse and session are in green boxes, and neuron is in a blue or a purple oval. Why do you think that is? Why do we think that neuron is represented differently from mouse and session? Nothing depends on it. So, so I'll get to, all right, excellent, excellent. I love our answers. So I'll answer John first. I'll answer John first, then I'll answer Mia, and then I'll get to Julian. So Julian says that neuron looks different because nothing depends on it. So that's a great thought, but if that were the case, if you recall yesterday when we looked at our diagram after we had created mouse and session, both mouse and session looked the same, even though nothing was depending on session at the time. So that's not quite it, because neuron doesn't create any new primary keys. So Mia, each table has to have primary keys, okay? But I love that you're thinking about it. And to get to Julian's answer, neuron is an imported table. Exactly, Julian. So we see that mouse and session are the same type of table. They're DJ.manual, they're manual tables. And neuron is an imported table. So as soon as you look at the diagram, you can see a wealth of information. You can see the direction of the pipeline. You can see how data is flowing. You can see what types of tables you have in your pipeline, and you can delve deeper into those and look at the columns in those tables. Okay. Do we have any questions so far? So I think we're good. And so now that we've defined neuron, let's look at neuron. Excellent. So we have our beautiful imported table. Of course, we haven't imported anything yet, but it's there. Yes. So as we said before, long blob, just to reiterate, the long blob data type is a data type that can store NumPy arrays. Right. And so, yes. Excellent. So now we can start importing the data into the imported table, okay? So rather than filling out the content of the table manually using insert one or insert methods, we're going to make use of the make and populate logic that comes from imported tables to automatically figure out what needs to be imported and perform the import. So what makes an imported table special and different from, say, a manual table is that it has what's called the make and the populate method, okay? The populate method and the make function, sorry. So as you might imagine, the populate method is there to tell DataJoint, hey, DataJoint, fill my neuron table up with data. So let's call it, and I would like you guys to run this in your own notebooks, but yes. And so when we call neuron.populate, what happens? We get an error, right? So DataJoint says, hey, we can't populate anything because we haven't defined our make function, right? So we haven't told DataJoint how to populate the table. And so what we need to do is we need to go back into our table definition. And apart from defining the columns, we have to tell DataJoint how it is that we want it to populate those columns. So yes, just below our columns, we'll define a function called make. And you'll notice that it takes the argument key. Whenever you're defining a class and you define a function within that class, you always have to declare the self, right? That's just like by default in Python. And so our real argument is key. And so what we're going to do in this make function is we're telling DataJoint to populate our neuron table. So that's where the self comes from. We're saying, hey, perform this function on itself on the table. And we're gonna populate our columns with the key, okay? And the key refers to our, primary key. And we'll talk a bit more about it right now, but let's look at how it works. So now that we've redefined our table, let's call populate again. So we say neuron.populate. And now we see, so in our function we had defined, we told it to print key is and define the key. So we see that we're printing key is mouse ID 0, session date, date time. So where is this key coming from? What table is this key coming from? Mouse ID and session date. Is that from the mouse table or is that from the session table? Mouse ID, session date. Where does this key come from? So give us a couple of seconds to think about it. All right, so as I'm sure we're thinking about it and we're looking at our table definition, we see that this neuron's parent table is session, okay? So neuron is dependent on session. And as we will recall, session had these two primary attributes as its primary key, mouse ID and session date. So when you call populate on an imported table, this triggers DataJoint to look up all the tables that the imported table depends on. For every unique combination of entries in the dependent or parent tables, DataJoint calls the make function, passing in the primary key of the parents. And because neuron depends on session, neuron's make function was called for each entry of session. So we can see that, okay? Excellent. And we can look at the session table once more. We can see mouse ID, session date. And so that's what was printed out here. And so note that make only receives the primary key attributes of session, but it doesn't receive the other attributes, okay? So now that we see the way the make function works, we're gonna really implement it now, okay? So the way it works is that it looks up the primary key of its parents table. Yes. And so, of course, we have our at schema, define our table or columns. And what we're telling DataJoint to do now in this make function, I know it looks long and a little daunting, but we're going to go line by line. So we're defining make. We use self and key, of course. And we're telling DataJoint to use the key dictionary to determine the file path, okay? So we're saying, okay, this is where the data is gonna be. Remember, the point of this table is to hold the data that we got from the sessions. So right now we're defining the file path and we're using that dictionary unpacking and the format method for all the keys. So as DataJoint is calling the key, it's something that it's going for, so for each key, you're defining your new file path. right? And what you're going to do is you're going to load that data file. Okay. So we're doing two things already. For each key, we're defining a new file path. We load that data, and then we have our for loop where we'll say for index and D in enumerate data. And for those of us familiar with Python, this enumerate function here, it creates like an index for the in this case for the data. So for index and D in the data, we're gonna add the index to the neuron ID column. Okay, and we're gonna add the D, which is the data, to the activity column. Okay, and so once we've enumerated this data, we'll use a self.insert1 key. So, and at the end, we're going to print populated neuron, and we'll use the same, our little hack that we've used right here, which is neuron ID. So we populated neuron ID for mouse ID on session date. Okay. And so let's run it. We'll get a better understanding. All right. Thank you, Julian. Thank you. We'll see you tomorrow. Please be sure to stop by. Yes. So notice that we added the missing attribute information activity into the key dictionary, and finally inserted the entry self equal neuron table. Yes. The make method's job is to create and insert a new entry corresponding to the key into this table. So we run this, or new definition. And so as it's inserting, neuron is also going to be printing out the results of what it is that it's populating. All right. So we called populate and it told us, all right, so no complaints. So it says it populated for neuron 0, neuron 0, neuron 0, for mouse 0. Okay. So it populated for these neurons, for these mice, for these sessions. And can anyone tell me why, well, it's gone now, so that's okay. All right, so now we run neuron and we see that our table has been populated, right? With all the data from its sessions. So for mouse ID 0, we have the session date, the neuron ID, and the activity. And this is going to be my question. Why are all the neuron IDs 0? Why aren't they like 1 or 2 or 3? What does the 0? So we know that when Python indexes, or in programming, whenever you're indexing, you start from 0, right? So the neuron IDs are 0. And so what does this tell me? The fact that all the neuron IDs were 0. What is this telling me about how many neurons we collected data from in each session? Right, exactly, John. So every data file is just one neuron. Excellent, excellent. So obviously, as you can see, we only have one data per neuron session. And so what happens if we call neuron.populate again? Nothing, right? And this makes sense because we have imported neuron for all entries in session and nothing is left to be imported. And so what happens now if we insert a new entry into session? So we have a new entry in session, and we can find all the sessions without a corresponding neuron using our negative restriction operator. And so that's our session. And so now we'll call populate once more. We'll pretend that Jacob did everything right and he did his session and he put the data where it's supposed to be. Excellent. So we see that neuron just populated the data from this new session. And that was neuron 0 for mouse 100, session date the 1st of June. Excellent, excellent. All right, so summary, congratulations. So now we've extended our pipeline and with a table to represent this recorded data. And we've learned to implement the make we've learned to implement the make function and the populate function to load external data into your tables. Beautiful. So now that we can see how we're constructing our pipeline, we can see how everything's related. Everything is, these downstream tables are dependent on the upstream tables. We can see the power of automating that import of the data. And so as long as you define your tables well, it's a breeze. And so now we move on to notebook 3. Yes, a bit confused about why the populate call leads to being run. Would it run all functions within neuron? So within the definition of DataJoint, calling populate makes the make function run. That's just like the point of the populate function. Does that make sense? Yes, so yes, because all of this is defined under the make function. Okay, so within the make function, we told DataJoint that whenever you call populate, you're gonna get a data file, you're gonna call the key, or you're gonna get the key from whatever is upstream, and you're gonna create a new data file path. You're gonna load that data, and then you're gonna have an index, and you're gonna have your data, which you're gonna insert. Okay, so this make function is the way you automate just importing all your data into the table.
Maybe
Yes.
I can add a bit of a clarifying information here. So
Please,
the make function is basically how you define how a table should, quote unquote, make itself, right? How should the table would know how to, prepare the data and insert into itself.
Right.
DataJoint has a auto populate routine that's whenever you call dot populate, the dot populate logic figure out what has already been inserted, what's left to be inserted, and then call the make function only on the ones that has not yet been inserted.
Right.
So that's like two-step process here, right? The populate, which is the auto populate routine that DataJoint knows how to, orchestrate the work, figure out which one missing, running, kind of like a job reservation kind of mechanism. And then the make function is something that each user can write to define how that function go about making the data for it and insert into itself. Yeah, so
yes.
Right. So the populate call is being driven by, calling the make function, but as you say right there, right? Populate call is actually what calling the make function one by one.
Yeah. Yes. Awesome. So thank you, Tin, for that. And thank you for your questions, of course. Please keep them coming. We love that you guys are learning. And the goal here is for you to be able to go out and get to data jointing. So now we get into our final notebook for this session, notebook 3. And let me scroll to the top here. And so we'll be working with automated computations, okay, or computed tables. So in this session, we're going to learn to compute various statistics for each neuron by defining a computed table. We're going to define a lookup table to store parameters for computation. We're going to define another computed table to perform spike detection and store the detected spikes. We're going to automatically trigger computations for all missing entries with populate. So that's what we just spoke about. And we're going to define a part table to save the results computed from the master computed table. So we have quite a bit happening here. So strap in. So we import DataJoint. and we import NumPy and Matplotlib, just like before. And so the last time from our tutorial pipeline package, we imported schema, mouse, and session. Now we're going to be importing schema, mouse, session, and neuron. Okay. So just to look at it, these are our tables, just as a reminder. We have session, we have neuron. Yes, it's blob. All right. And so the ephys cell activity.py package also fills each table with data and imports the neuron activity from the NumPy files to make sure that we're all on the same page. So much like we did in Notebook 2, where, we're filling all the tables with the data, with all the same data, so that we don't have to define anything, we don't have any differences, so that it's pretty standard and uniform. So now that we have successfully imported all the data into our into our pipeline, it's time for us to start analyzing them, right? So we've done quite a bit of, we've done the heavy lifting in terms of defining this data and getting it in, but now that we have it there, we want to analyze it. We want to see what our experiment revealed. So when you perform computations in the DataJoint pipeline, you focus and design tables in terms of what it is that you're computing rather than the how. So you should think in terms of the things that you're computing. Now, let's say that you want to compute the statistics such as mean, standard deviation, and maximum value of each of our neurons' activity traces. Hence, we want to compute the neuron's activity traces for each neuron. So the thing or the entity here is activity statistics, where each entry corresponds to the statistics of a single neuron. Let's start by designing the table, paying special attention to our dependencies. All right. So, like we did in the last notebook, we define our key, and we'll restrict by this key. In this case, we're using the 0th key inside our. So we're using basically the first row. Okay. Yes. So let's go ahead and grab the activity data stored as a NumPy array. As we learned from the last session, we can fetch it. Okay. So remember that, and this is something new. I touched on it in the last notebook, but in the same way that we can fill in like the key, we can tell DataJoint, hey, just fetch the key. You can also fetch different columns. In this case, we just want the activity. So we just want this blob, right? This NumPy array. All right, beautiful. So we get an array of an array, right? So a fetch returns your NumPy array. And so even if the attribute is a NumPy array, we have an array of an array. So we're gonna index into this array. So we'll say activity 0. Now we have our data. And of course, if we knew that there was only one item, we could use the fetch 1, which would save us a bit of time and trouble. So there we go. All right. So now we can compute some statistics. Okay. So now we can compute some statistics. Now we have our arrays, and we want to see things such as the mean, and we want to see things such as the standard deviation and the maximum. And so we know that this is an array, and so we have certain NumPy methods that help us out. If we're not as familiar with NumPy, I'm gonna show us how it works. So if we define mean, if we want activity, right? We'll have this variable, and we just want the mean of it. The array is in this activity variable. So we'll say activity.mean, we call it, and we'll just call mean. Awesome. So here we have the mean of all these numbers inside the array. Okay, so that's our first statistic. If we want to call the standard deviation, or if we want to define the standard deviation or compute it, we would do the same thing, but with we use STD. So I'm going to give you, and if we want to compute the max, we'll do the same thing, but using dot max. So I'll give you guys a minute to do it on your own. And when you have it, please, someone paste your code in the chat and we can run it so that everyone can see. Give you guys a minute. So again, for standard deviation, you would call .std, the array .std. All right, so we have about 40 seconds. Again, please feel free to, once you've got it, please feel free to paste it in the chat and we'll run it. All right, so in about 20 seconds. All right, we're at about 5 seconds. Okay, so do we have anyone who figured out how to compute the standard deviation of our activity? Or anyone who figured out how to calculate or compute the max of our activity? All right, Mia, thank you. Okay, so, all right, so that's one way, yes. So let me do this. Oh. Thank you, Mia. Mia said this is one way to do it. All right, and for max, we could do this. All right. Did anyone else do it in a slightly different way? Maybe a bit closer to how we did it here. All right. Thank you, John. So John says he did it this way. Oh. Awesome. That's a great, excellent, excellent. So, and that's how I would do it. So while both are correct, that's how I would do it as well, right? So I would say std underscore activity is equal to activity.std, and then we just call it, right? Excellent. And then for max, same thing, max underscore activity. Excellent. So this gives us a good idea on how to fetch the activity of the neuron, knowing its primary key, and compute interesting statistics. So now that we know how to compute these statistics, let's go ahead and define our computed table. So, of course, we have our table definition. I think at this point we have it down pat. So we let DataJoint know in what schema it's going to go in. In this case, it's going to be schema. We know that we let it know that activity statistics is dependent on neuron as its primary key. And we know that, or we're telling it that we'll calculate the mean, which is going to be a float, standard deviation, and max. And of course, I left this part for last. So we've seen the DJ dot manual. We've seen DJ dot imported. Now we're seeing DJ dot computed. So we define our table. Yes. And so now what we're going to do is we're going to look at our diagram. Okay. Now we have our beautiful pipeline just really taking shape. So we see that each table downstream is dependent on the table upstream, right? And so what do we notice about this specific diagram? Why is it different from the previous diagram? Why do you type diagrams today? Yes, so yeah, they are the same, John. That's a great question. And as I said yesterday, you can use either one. Diagram is just the more modern way that we've been doing it. It's just a little more, I guess, it just feels more natural to me to remember a diagram because I want to see a diagram versus .erd, but it's the same thing, yes. But what do we notice that's different in this pipeline? Or as compared to, in this diagram, I mean, as compared to the last diagram that we saw? Yes, ERD stands for Entity Relationship Diagram. Yes, thank you, Tim. Right, and so I'll be using diagram and ERD interchangeably. And so, yes, so activity statistics. Right, but so the question, Mia, is in terms of our diagram here, what do we notice that's different? Just visually speaking, just giving it the eyeball test, what do we see that's different? Or what new element has been introduced? Oh, you're saying activity statistics. Okay, yeah. So the activity statistics table was introduced into our pipeline, of course. And since it since it is a computed table, thank you, Mia. Since it's a computed table, which is different from an imported table and manual table, it's represented differently. Excellent, excellent. And so just like the imported tables, computed tables make use of the same make and populate logic for defining new entries in a table. So as we were defining the table the first time, we told DataJoint it's a computed table, and we put in the columns, right? The primary attributes and the secondary attributes. But now we're gonna actually define our table, define our table's make function so that it can populate. So, and this is what I need you guys to do for me. Well, we've already pretty much done it, but we have our columns, and as we define the make function, we get our key, of course, and we're telling DataJoint to restrict the neuron table by the key, and we only want to fetch the activity from that column, from that entry. And so that's going to be equal to activity, okay? So we're telling DataJoint to look in the neuron table here, right? Which is its parent table. And we're telling it to only return the activity information. So only return the blob. That's all we need right now. So we're saying, hey, DataJoint, whenever you whenever you populate your data, what you're going to do is you're going to look into the neuron table, restrict by key, and we're going to look into the neuron table, and we're going to get the activity, and then we're going to compute 3 different things. And so as we did earlier, we're going to be computing the mean. We're going to be computing So if you recall, to do that, we said activity.new, right? To compute the standard deviation, we say activity.std. And just making sure we'll do activity.next, right? And so we're saying once you've computed these, you're gonna insert that data, you're gonna insert your computations into the table, and you're gonna print computed statistics for mouse ID and session date. So let's run it. Awesome, DataJoint didn't complain, we didn't have any errors. So let's go ahead and populate the table. So of course we run the .populate, which is gonna call this make function. Awesome. So the fact that it's printing out everything tells us that, it worked. So let's look at our activity statistics table. And voila, you have computed your statistics for each neuron activity. So we have our primary key, right? Which is based on neuron's primary key. So it's mouse ID, session date, neuron ID. And we have our computed statistics for each neuron in each session. So we have the mean, the standard deviation, and the max. Excellent. So how are we feeling? Do we have any questions, any concerns, any thoughts? All right, so I take it that we're okay. Tin or Kavi, do we have any comments or anything to add before? Okay, what if you were to make activity session an imported table? Would there be a problem?
Yeah, maybe I can take that.
Yeah,
if you don't mind.
Yeah.
So Mia, great question. Not really, no, because imported table and computed tables are really the idea behind those two are that they do have this auto populate and mechanism and make functions. They behave the same way. So to answer your question, no, there wouldn't be any problem at all. The reason why we are denoting things as imported table versus computed tables are for several reasons. So imported table represent tables that would require kind of like files or raw data files somewhere that you have to have access to be able to import. So in the sense, those are more valuable, right? So in the, you can move the data away after you ingest the data, things like that, right? So imported tables denote that type of activity where you need access to some external files or something. Maybe you mount a drive on your machine or something like that to be able to import, to be able to call populate on. Computed tables are more that for those tables that are entirely computed tables, right? So you can compute the result all within from the upstream table all within the database. So you don't need access to the external. You can, unplug your drive or whatever, and you can still be able to, populate those tables. So that's really the distinction there. And because of that distinction, it also makes data backup an easier task, meaning the worst case scenario, you don't want to lose your imported data. You don't have to back up your computed table as regularly because, worst case scenario, you can always recompute them, right? But you don't want to, so imported tables are very, very, very valuable. You don't want to, so you may want to back them up more regularly. That's kind of like more on database management kind of thing and data management aspect as well. Yeah.
Right. And so I think the kind of concise answer of what Tin was saying is that like imported and computed tables and in the background, they're pretty much, they're the same, but the distinction is more so for database management and just for clarity of your workflow, right? Yes, awesome. Awesome. Do we have any more questions before we move on? Are we okay? Do we want to take a minute or two to stretch our legs? Or so we're on our last stretch right now, pretty much. So if we want to take a minute or two to just kind of stretch a little bit, let's get some water real quick, run to the restroom real quick, just let me know in the chat. All right. Yeah, let's take it to, yeah, I agree, Tim. So we'll take a quick 2-minute break. It is 12:25 our time right now, Central Time. So we'll be back in 2 minutes, okay? 12:27 our time. All right, so we can all kind of come back. I hope you had enough time to get a sip of water. And as I said before, we're on our final stretch. So now just to recap, we've created our manual tables. So we've started our workflow. We've defined, our mice. We said, okay, we have these mice. We've defined the sessions that they're undergoing or they've undergone. We've defined the neurons that were observed, and we had the data. And then we defined the table to compute different statistics on that data. So we have 4 tables in our pipeline so far. And so now we're gonna take it a step further, and we're gonna get into spike detection. Okay, so just as a quick caveat, now we're gonna be using quite a bit of matplotlib. And so if understand that, of course, you know, matplotlib, you use it quite a bit as you're performing, as you're creating your visualizations, but it's not like explicitly, it's not specifically DataJoint, okay? But we're using matplotlib as our visualization library. And so if you're not as familiar with the syntax for matplotlib, don't worry. But yes, please feel free to ask any questions or voice any concerns or anything that you may have. So what we're going to do now is, yes, it says, while having raw neural traces in itself can be quite interesting, nothing is as exciting as spikes. So in neuroscience, we love looking at spikes. And so the first thing we're going to do is we'll get all the keys from the neuron table. So we'll do a neuron.fetch. And then we're going to fetch all activities we're going to fetch all the activities and put it inside the activities variable. Okay. So we get to this first part that I was talking about as far as the matplotlib. And so we're going to start our first visualization. And so what we can see here is a visual of the arrays that we had gotten, the blobs, right? And what we did is we told matplotlib to create 5 subplots. And we said that we want our axes to be time and activity. And yeah, I don't want to get too much into matplotlib, but long story short, we've defined how to create these plots. And so we can see that this is the visual representation of those arrays that we got, of those blobs. So now what we're going to do is we'll focus on just one trace. So we'll use key 0. And we're doing the same thing, of course. We're using fetch 1 since we only want 1. And so now we can zoom in quite a bit more. And so we can see that we have our spikes, but what we need to do now is define a threshold to detect when a spike officially occurs, okay? So we'll use 0.5 as a threshold. And we see that we're superimposing our criteria for a threshold over what we consider over the raw activity. So we're saying that anything that goes above this point is considered a spike, okay? And so we want to find out when it crossed the threshold. That is, find the time bins where above threshold goes from 0 to 1. Okay, so basically we're trying to detect, was it a spike or no? And so that's why we have our threshold. So yes, again, we're telling matplotlib to place these dots kind of to which helps us visualize better whether to visualize better where our spikes are, okay? And so yes, we can count those. So we can, based on our threshold, we can see how many spikes we had across a certain period of time. So yes. And so now what we can do, and this is where you guys get to put in your own threshold, because ultimately we're trying to figure out what the best threshold is to define what a spike was and what wasn't a spike. Okay, so as we defined it the first time, we said that our threshold would be 0.5, which is a good start, but maybe you want your threshold to be higher, or maybe you want your threshold to be lower. Can anyone suggest a threshold that we could put in here? So maybe we don't want to use 0.5, maybe we want to use a different number, maybe a lower threshold, 0.4, maybe a higher threshold, 0.6. What do we think? So I'll put a higher threshold And so, 0.6. And we'll see that as we define it, well, our spike counts remain pretty much the same. So maybe let's just see, just for the sake of argument. Right, and so we see that as we lower that threshold, we got 38 more spikes, okay? Meaning that as we're defining our threshold, we're basically saying, okay, at what point does, a trace, at what point does this trace, is it considered like a spike where the neuron actually fired, okay? So now notice that the exact spikes you detect depend on the value of the threshold. Therefore, the threshold is a parameter for our spike detection computation. And rather than fixing the value of a threshold, we might want to try different values and see what works well. In other words, you want to compute spikes from a combination of neurons and different threshold values. To do this, while still taking advantage of the make and population logic, you would want to define a table to house the parameters for spike detection in a lookup table. So far, we've manually been putting in what this threshold for what's considered a spike to be. But the point of DataJoint is to automate much of your processes, right? To automate this workflow. And so apart from having our manual table, our imported table, our computed table, we also have what's called a lookup table. And the threshold here was what we call a parameter, okay? And so the purpose of a lookup table is to store different parameters. So we're gonna define a table called spike detection param. So the name is pretty self-explanatory, to hold a different number of parameter configurations for our spike detection algorithm. We're going to define this table as a lookup table rather than a manual table. By now, you know that lookup must be yet another table here in DataJoint. Lookup tables are depicted by gray boxes in the ERD. All right, in the entity relationship diagram. And so this tear indicates that the table will contain information and that will be referenced by other tables. So this type of information doesn't change much. And so it's more so of that metadata type, okay? So we define it, and a lookup table is quite similar to a manual table. So we use our dj.erd or dj.diagram, and we can see our gray box right here telling us that spike detection param is a lookup table. So we have our manual tables, we have our imported tables, our computed tables, and our lookup table, parameter lookup tables. Okay, so now let's take everything together and define the spikes table. Here, each entry of the table will be a set of spikes for a single neuron using a particular value of the spike detection param. In other words, any particular entry of the spikes table is determined by a combination of a neuron and spike detection parameters. So you see how we're automating the way we determine what we consider and don't consider spikes, right? Using these different tables. So we capture this by depending on both neuron and spike detection param. And for each spike set, we want to store the detected spikes in the total number of spikes. The table definition will look something like this. So since we said we're depending on the neuron table and spike detection table, right? So we have our arrow and we say we're depending on neuron. We're also depending on spike detection param. Okay. Excellent. So we've defined this table. And so I just want to emphasize the fact that prior to defining this table, our ERD. There was no connection here, right? Because nothing was depending on it just yet. But now that we have a table that's dependent on it, we can see the line telling us that there is a dependency there. So define the waveform part table. So we would also like to store the waveform of each detected spike. And so it gets even cooler, right? So after we've defined what is a spike, so after we've determined where our spikes are, we want to store those waveforms and for a particular neuron. For simplicity, let's define the waveform to be 40 sample points before and after the onset of the detected spike. So to accomplish this, we will define a dj.part_table waveform, which will be called a waveform, and this will contain the waveform per spike. And like we said, this waveform will be 40 points before and 40 points after what was considered the spike, okay? And so we said that we define a table using class, and when defining a part table, you put it within that definition of the master table, and you let DataJoint know that it is a part table by using dj.part. So our main table or master table is the dj.computed table, which is dependent on neuron and spike detection param, right? And so we're calculating what the spikes are, or computing what the spikes are, and we're computing the number of spikes based on our criteria. And then we're going to be storing the spikes and their shape. We're going to be storing them here in this attribute as a waveform, okay? And so a part table, as we had told Mia earlier, each table has to have, or each table has a primary key. And so here we're saying that waveform is dependent on master, and it also has another primary attribute to make up its own primary key called spike ID. Right, so the arrow.master syntax denotes that waveform is a part table. So all of these kind of clues let DataJoint know that it's a part table, right? We're literally saying it's a part table, but we also have master to let it know it's a part of this spikes table. And it said the master syntax denotes that waveform part table is a foreign key constrained by spike table. And this master table drives the populate logic. And the content of the part table is generally ingested together with the content of the master table all in one step. And so we see a very powerful aspect of DataJoint where, so waveform, the waveform table is a part of the spikes table, which is computed. And when you call the .populate method on spikes, it's gonna fill up both tables at the same time. So let's look at our diagram. And so we see this beautiful diagram here. We have our manual table or imported table or computed tables, our parameter tables or lookup tables, and we have our part table. And as I said before, DataJoint is extremely visual, which is something, one of the many things I love about it. And so we can see how our pipeline, how data is flowing through our pipeline, okay? So we can see that from this neuron table, when we imported data, we're calculating activity statistics. We're also calculating spikes from this neuronal data. And from that, from the spikes, we're computing what we consider to be waveforms using our parameters. Right. So now we're going to go ahead and implement the make method for the spikes table. And so, as you might imagine, it's a little bit more, it's a bit longer, but you know, the logic stays pretty much the same. Look at the time here. Okay. So we define our make function. So we have our master table, we have our part table, and now we'll define our make function. So the first thing we'll do is we'll say print populating for and populating for the key. So the first thing we do is we define activity, right? And we've seen this quite a bit now, which is restricting the neuron by the neuron table by key and just fetching the one activity in this case. Or fetching each activity for each key. We're also defining threshold, which is using the spike detection parameter table restricted by the key. And again, that's using another fetch one. And all we want to fetch there is the threshold. So what we're saying is that we're going to be using all the thresholds that are in the spike parameter table. And so we're defining above threshold as activity greater than threshold as type int. So we're saying that this variable is going to be an integer. And so then we also have rising, where we'll say this is the difference. Yes, finding the rising edge of the crossing threshold. And we're also defining spikes, which, we're also defining the spikes, okay? And then the count is going to be the sum of all those spikes, of course. We're also going to be printing detected, the count, detected how many spikes. And then we're going to be inserting this data into, it's going to be inserting this data into itself. Finally, then we'll extract the waveform, whatever was considered a waveform, we'll extract it and put it into the waveform part table. Okay, so we said that for our spike waveform, we'd be using 40 sample points before and 40 sample points after. And so basically that's what we're doing here. Again, I'm trying my best not to go too much into the NumPy and matplotlib syntax, just because it might be an additional level of kind of complication, but that's what we're doing here in a nutshell. For simplicity, skip the spikes too close to the beginning or the end. Yes. And then, so we're saying the waveform is going to be equal to the activity of the spike minus the before spike, and the spike plus the after spike. So it's something that we probably won't have enough time to fully explain, but understand that in our make function here, we define, we're getting the activity, we're getting the threshold, we're defining what's considered as above this threshold. We're defining what's considered a spike, where the rising part of that threshold is, and then we're counting what we had considered to be spikes. So we're inserting that into that master table, and then we're inserting the data, the spike data, whatever we consider to be a spike, we're inserting it into this part table. So as we define it, it says yes. So we'll define it. Awesome. And so we didn't get any errors, so that's good. And now we're going to populate. Okay. And if you'll recall, we'll call spikes.populate. This doesn't seem to do anything. So why don't we think that it is populating? So why don't we think that the table is populated just yet? So if we go ahead and look at our table, we know that spikes is dependent on neuron and spike detection param, right? We know that it's dependent on these two tables. Would that have anything to do with the reason why it's not populating? Remember, we said that when you call the .populate method in a table, DataJoint goes and looks into the parent tables to get those keys. Is there something that we're missing from any of these tables? So let's think about it for a sec. So we defined the tables, right? And we populated neuron, but what about spike detection param? Did we do anything with that table? All right, so I would imagine we're trying to remember. So let's look at spike detection param. Let's see. So if you notice, it's an empty table, right? There's nothing there. So of course, if there's nothing there, DataJoint can't get anything, right, from nothing. So what we need to do is we need to define some parameters. We got to tell it, we got to give it a threshold, right? So we're going to insert 1. We're going to insert 0.5 as our first parameter. Awesome. And so now we should be ready to perform the computation. So let's do spikes.populate. All right. So it says populating for, and now it told us based on our threshold, it's saying that for our first neuron in our first session, it found 26 spikes. For a second session, it found 24. For the third, it found 18. For the fourth, it found 41. And the last, it found 18 spikes. Awesome. Now here we go. And so do we have any questions on how this ended up working, or is it good so far? All right, so I think we're good so far. And so now what we can do is we can build, now that we have our table, we can query and we can look at the spikes for the different, we can look at the waveforms of the different spikes. So it says, let's build a query for waveforms from mouse 100 session, and the session that took place on the 25th of May, 2017, with a spike detection parameter of 0. So let's build that query. I'll give us a minute to do so. Naturally, I'm almost out of time. So we're gonna do, let's see. We're just gonna do 1, okay? We're gonna say, so we only want the waveforms. So the way we do this is, we call our main table spikes, and waveform is a part table. So we say spikes.waveform, and we're restricting by mouse ID is equal to 100, and session date is equal to 2017 05 25. All right, and SPD, spike detection parameter ID, is equal to 0. Oh, thank you, John. Let me see. Let me just run it real quick. Oh, let me see here. Oh, SPD ID. I'll fix the bar in a second. Give me one sec. Let me see. I'm not sure. Well, all right, so that's a bit better. Make some space right here. All right, so let's try this again. SDP, I'm sorry, it's a type, spike detection parameter. Excellent. So based on our query, right, we wanted the waveforms for mouse ID 100 for the session date, for this specific session date, for spike detection parameter ID 0. And so these are all the waveforms that we got. Okay, remember that it said that for that first, for mouse 100, for that session date, there were, that's 41 spikes. Let me see. All right, so, and so because of time, we can, I'll have to, you guys can do these two on your own. You can practice. And if you want to check on the answers as far as how to do them, you could go to the completed directory here, and you could see what it is that we had expected as far as the code to get the appropriate output. So we could also, just very quickly, we could have added, new parameters inside the spike detection param table. And, we could have done the same thing. And so finally, of course, you can delete entries upstream. And we saw that yesterday where you can use the uQuery, and then you can call the delete method on that, right? But yes, for right now, we'll leave it as is. Yeah, and remember that DataJoint, when you call the .delete, it tells you where data is going to be deleted from, all the dependencies, and it'll ask you, are you sure you want to delete this? Yes or no. In this case, we'll say no, right? And you can delete data from any table. So congratulations, you've successfully extended your pipeline to a table, with a table to represent recorded data, neuron as to represent recorded data, with tables that perform and represent computation results, and a table to hold computation parameters, so a lookup table. Okay, and we'll get one last look at our, pipeline. So it is a beautiful pipeline. And I hope that you guys, thoroughly enjoyed that. And please, as I said earlier, please feel free to go back after the session, and we have different, this is for our array EFIS, but we also have our calcium imaging activities. So you can go through those and you can learn, you not only learn DataJoint, but you learn more neuroscience. So thank you very much. Do we have any questions? Thank you, Tin. And before we go, I want to provide a few links. So we have our docs, of course. Thank you so much, John. I appreciate it. Thank you, Tin. Thank you, Kavi. So we have a few links. We have our docs. We have our Git. Oh, I didn't even. All right. Yeah, we have our GitHub. Thank you so much, Mia. We have our company website. Get those. And so please feel free to visit all our resources. And please feel free to interact with us, where we love getting new users. And, of course, we love making DataJoint grow and improving it. So thank you guys so much. I'll stop sharing. And Tin, Kabi, I'm not sure if anyone has anything else they want to add or. All right, thank you, Kabi. Oh, so as far as tomorrow, that's a great question, John. So Tin is actually going to be our leading our workshop. And so it's going to be a great workshop. He'll be going over a specific workflow, the workflow array ephys. So he's going to get more in depth with that. So what we did today was understanding how to use more so the framework, understanding the syntax, understanding how things work. But Tin's gonna take this workflow, the workflow array ephys, even deeper. And so it'll be a deep dive into that. And then on Thursday, as we said, Kabi is going to be showing specifically how to set up DataJoint and how to set up all things DataJoint related on your local machine. So you don't want to miss those. So please make sure to show up tomorrow and Thursday. Awesome. Thank you. Thank you.
Thanks, David. Then I will stop the screen.
All right. Thank you.
See you tomorrow.
Thank you. See you tomorrow.